The title for our project is Convolutional Neural Network-Based Model for Patient Representation Learning to Uncover Temporal Phenotypes for Heart Failure. Heart failure is a major problem in the US, affecting millions. Its high morbidity and mortality rate costs the country about $31 billion a year. In order to alleviate this issue, we wanted to develop a way to detect or predict heart failure earlier and better characterize heart failure for more effective treatment. We based our approach on the word-to-vec model in Mikolov's paper, as well as using CNN in the context of NLP in Kim's paper. Word-to-vec transforms events into distributed embedding forms that contain hidden semantic relationships between the events. CNN takes in a sequence of events to predict risk of heart failure and automatically learns latent structure in sequential relationship between events. We wanted to improve upon previous work by Che by using time tokens, which indicate time gaps between the events. We also wanted to include demographic information as features in hidden layers for the CNN. And we also wanted to extract phenotypes from the hidden representation. Here is a brief overview of our model structure. We used a MIMIC-3 dataset, which includes over 40,000 patients from critical care units at Beth Israel Deaconess Medical Center, and the dataset spans 12 years. We selected our case patients by filtering for patients who had heart failure-related ICD-9 codes. Our desired observation window was 2,000 days with a prediction window of 90 days. We only included patients who had between 30 to 500 events within the observation window, which gave us a total of 651 case patients. And then we randomly selected twice that amount for control patients. We created several versions of the data to work with, those with event counts versus word-to-vec representations, those with and without time tokens, and another set with and without demographic data. Word-to-vec takes in time series of events for a patient like a sentence and outputs each event as an array of embeddings. Events for a patient are stacked into a matrix in temporal order to input into CNN. Since CNN assumes that each entry is uniformly distributed, we compensate by adding in discretized time tokens. Our CNN consists of 16 filters with sizes ranging from 2 to 5, giving us 4 channels per kernel size in the convolution layer. This is followed by 1 pooling layer and 2 fully connected layers. The activation function in the convolutional layers is the rectified linear unit, while the activation function in the final fully connected layer is sigmoid. We used Nesterov Atom as optimizer, and we implemented this in Keras with TensorFlow as the backend. We split our dataset into 7 to 1 to 2 training, validation, and test sets, and we measured the model performances by accuracy and AUC. We compared our CNN approach against a few baseline models, and we used TSNE algorithm to visualize patient representation learned from CNN, which is the output of the pooling layer. In this table, we can see that CNN performs better than baseline models. Models with time tokens also perform significantly better than those without. We also see that CNN, using demographic features, performs the best overall. This graph shows how well CNN is able to separate out the control and case patients using the embedded representations. The table on the right gives the top 10 most indicative features of heart failure for each type of event. Now we will move on to talking about patient phenotypes identified by CNN. The graph shows the separation of the 3 phenotypes obtained by k-means clustering. We found that clusters 1 and 2 were quite similar, but at the same time, they were also distinct. Both groups seem to have heart failure related to diabetes, but cluster 1 seems like it was at a later stage than cluster 2. Cluster 3 seems to be unrelated to diabetes and is actually related to high blood pressure-induced heart failure. So to conclude, we found that we successfully implemented a CNN method through extracting temporal information from EHR data to predict heart failure. We also found that CNN could be a highly effective model for healthcare data mining. Also, we found feature engineering is crucial, especially with the inclusion of time tokens, which largely improved the prediction performance. And we were also able to elucidate phenotypes and also identify salient features. Some future directions for this project, we would definitely like to apply this methodology to a larger database with more extensive patient history to predict for general populations. We also would like to generate more refined phenotype representations, which may be useful in facilitating treatment of heart failure patients.
Thank you.
Thank you.